Brody has 384 feet of fencing to enclose a rectangular area and then divide it into 3 equal-sized pens to separate the males, the females, and the lambs at an auction. What is the largest possible total area of these 3 pens? So in this problem, we are trying to find the largest possible area. So we are looking for a maximum. So I always like to begin by actually writing down my goal. And in this case, our goal is to maximize the area. So we want to find a maximum area, which means we need to write an area equation. And in order to do that, we need to start with a picture. So it says Brody has 384 feet of fencing to enclose a rectangular area. And then that rectangle is going to get divided into 3 equal-sized pens. So let's try to draw a picture of this scenario. So we have one big rectangular area, but then he's also going to use the fencing to divide this big rectangle into 3 smaller equal-sized rectangles. So our picture will look something like this. And if our goal is to maximize area, then we want to write an area equation. And this is the area of a rectangle. And we know the area of a rectangle will be length times width. So let's label the length and the width on our diagram. So I'll use L for length and W for width. So therefore the area of this rectangle is length times width. However, we can't maximize this area function because it has too many inputs. We have 2 inputs, the length and the width. We need 1 input and 1 output. Therefore, we need to come up with another relationship between the variables that will allow me to eliminate either the length or eliminate the width so that we only have 1 input. So I call this writing a constraint equation. We want to reread the problem. We want to see what constraint are we working under. Is there some sort of a limitation in this problem? And it says that Brody only has 384 feet of fencing. So that 384 feet of fencing, that's our constraint. He doesn't have any more fencing than that. So we need to write an equation that will be equal to 384, and this is going to represent exactly where the fencing is going to go. So back to our diagram, we know that the fencing is going to go around all 4 sides of this bigger rectangle. So if I continue to label the sides, we know we have another length and we have another width. But in addition to that, we have to put fencing down the middle in 2 places. So that means we're going to be adding an additional width 2 more times. So all together, if we add all of that up, we're going to end up with W plus W plus W plus W, which will be 4W, plus L, which is 2 L's, or 2 lengths, and that will all equal the 384 feet of fencing that he has available. So this is our constraint equation. It's a second equation that relates the variables. And then you can choose here whether you want to solve for W or solve for L. It does not matter which one. I always recommend that you just solve for the one that might be easiest. In this case, I'm going to solve for, I'll solve for L. So we'll have 2L is equal to 384 minus 4W, and then divide by 2. So L is going to equal 192 minus 2W. And I always like to make sure I box this equation because this is a good relationship between the length and the width in this problem. And then we're going to use this equation and substitute into our area model to eliminate one of our variables. So now our area, which used to be length times width, it's now going to be the quantity 192 minus 2W times the width. And I'm going to go ahead and distribute. So that's going to be 192W minus 2W squared. And this is going to be our area model. And you see now how we have one input. We're inputting the W, the width, and then our output is going to be our area. So this is a function that we could, hypothetically, we could graph this function, and we could certainly think graphically. In this case, we know this function is quadratic. It would be a parabola, and it would be one that opens down because we have a negative leading coefficient. So we see that the maximum there, the maximum is going to be reached at the vertex. But if we want to put our calculus knowledge to use, we know that that maximum in this case is going to be where the slope is equal to 0. So we're going to be looking for our derivative and then setting our derivative equal to 0. So this is the process called finding critical numbers, which we've done in past sections. So let's go ahead and compute the derivative of a, so a prime, which will be 192 minus 4w. And then we're going to set that equal to 0 because we're looking for when we have a slope of 0. So 192 minus 4w equals 0, and then solve for w. So negative 4w equals negative 192. Therefore, w will equal 48. And if you read back the units on the problem, Brody had 384 feet of fencing, so this will be 48 feet. Now, we want to verify, I always want you to verify that this value actually yields a max. In this particular case, because the area function is quadratic, you're guaranteed that it's a maximum, but I want to go ahead and model how we verify. And essentially we're doing the first derivative test, and we would be testing around 48 to verify that we do indeed have a maximum. In this case, since w is the width, we would not have any negative values. Those don't make sense in the context of this problem. So I sometimes like to put that restriction on my number line and just put an X there, so I remind myself there would be no need to test any values smaller than 0. So I would test some value in between 0 and 48, perhaps 1. And then I could also test a number larger than 48, like 50. And then remember, these test values are coming back here into our derivative, so we can figure out the sign of the derivative. And if you substitute in 1 into the derivative, you'll end up with a positive value. And substituting 50 into that derivative will give us a negative value. So when the derivative goes from positive to negative, that means that the original function is increasing and then decreasing, and that is guaranteeing us that we have a maximum at 48. So now let's go back and reread the problem because we want to make sure that we answer the entire problem. And this problem asked for what the largest possible area was. So it didn't actually want the dimensions in this case. It actually wants the area. What is the largest area possible? So we need to take our 48, our width of 48, and then we would want to substitute that back here into our area model to get the actual area that is the largest possible. So we are going to be computing A of 48. And it would be fine to pause at this time, grab your calculator, substitute 48 into that area model. So A of 48, which will be the 192 times 48. Remember, you don't have to show this work because I would expect you to use your calculator at this time. So 192 times 48 minus 2 times 48 squared. And it looks like that works out to be 4,608. And because this is area, this would be square feet. So the maximum area, it's always a good idea to write your final answer in a sentence form when we're solving a problem that has a context. So the maximum area is 4,608 square feet in this case, and that maximum area will use all 384 feet of fencing that he had available.